As a reminder, it's easier to disprove that something is a linear transformation or a subspace, whatever we're trying to do, than it is to prove. To disprove, we just need to show a single counterexample, and that's usually the cleanest way to go. So in this case, the example from TBIL, they used just the vector 1, 1. Because they recognize that our problem here when we glance at this is this x squared term. And if we do any sort of scalar multiplication, if we multiply before or after we square something, it's not going to be the same. So we just need to make sure that we're choosing a value for that x that is not 0. Because 0 times anything is still 0, whether or not we have a problem with that linear transformation. So that's really the only thing we needed to make sure that we chose. The great thing about working in linear transformation land as opposed to when we were working with our subspaces is that we just need to make sure that we're choosing a vector to start with for these tests that is in our domain, right? So we can choose any vector. So here's the easiest way if we want to say is not. Choose a pretty easy to work with vector, some v from our domain, R2. And so, like I said, TBIL is used 1, 1. I realize the y is not going to matter here because nothing funkadoodle happens with y. So let's just choose the vector 1, 0. That is in our domain. It's in R2. You don't really need to state this because our domain is that entire vector space of two-dimensional vectors. It's not like the subspace where it's sort of like crucial that we say we started in the subspace and we're still in the subspace because we're leveraging that idea of closure and the definition of the space. But anyways, whatever. So our goal is to show that if we do some thing, let's say our scalar multiplication first. If I take some c times v, that this matters whether I do that linear transformation. Ooh, my s is getting a little integrally before or after. I want to show that these two things are not equal. And again, easiest thing here is just choose some value for c that's not going to be the same if I multiply before or after I square what's going on. So again, 1 and 0 would be bad choices for c. So let's choose our c to be equal, in this case, to 2. Because 2, if I multiply by it after the fact, is going to be 2. If I square it first, is going to be 4. Right? It's not going to be the same. So that's our c from our real numbers that we're going to use for our scalar multiplication. So what we'll do is we'll do s of 2 times that 1, 0. And we want to show that this is not the same as 2 times s of our 1, 0. Right, that this mapping, the order in which we do our mapping, our scalar multiplication, has an impact. So in this case, I need to know what s of 2, 0 is. Right, this is me doing the scalar multiplication first. Now I have to actually use the map, right, that rule that they've given me. And so this case, this will equal 2 and 5 times 2 squared, so 20. And I also want to do the other thing. I want to do s of my 1, 0. And I want to multiply by 2 afterwards. So let's leave the 2 on the outside. 1, 0 would be 1 and 5. And then we'd end up with 2 and 10. So at the end of this, though, we need to show, oh, right, now that I have this, I can see that I don't have that equality that I was looking for, right? That's one of those conditions. So now I've proven everything. I do have to state at some point that they're not equal to. Even I start with, oh, I want to show that they're equal to, like that's the goal, is to show they're not. And then I'm going to write my conclusion, and I'm going to just say S is not a linear transformation since it fails to preserve scalar multiplication. You can use the words preserve scalar multiplication. You could write out what we're testing. So instead of writing that, I almost forgot how to spell multiplication. You could have written out because, since, and we could have written just, not C, S of 2 parentheses brackets, right, does not equal 2 times S, right? So you can just write in words what it is, not in words, in math symbols, what it was that we tested as an alternate. But you do need this lovely conclusion. What did we find and why did we find it? We really need to make it clear what we were doing, like that this was all the stuff that was equal. Some folks, it was really hard to follow where your math was going. And if you really wanted to say anything about those values you chose, making sure that we are realizing that the vector that we're choosing to start with is starting in our domain, R2, and that we're choosing some scalar multiple. Now, if you wanted to show a failed vector addition, you could have chosen any other vector, like 1, 1, and then showed that if I do that transformation, if I do the vector addition before or after that mapping, this is not going to be the same. But again, we want to make sure that whatever we're doing here, that we're being clever and choosing values where I'm going to get out an x that is going to be different, whether I square and add or add then square. So in this case, 1 squared plus 1 squared is 2, but 1 plus 1 is 2 and that squared is 4. This would fail to preserve as well. If you do your work and it doesn't fail, especially on a question where they told you to disprove, that just means you chose poor values. But again, look back at your actual map and say, okay, I needed to choose x's that are different depending on when I apply either scalar multiplication or vector addition. All right, so that was B.